So now we're going to start getting into what an atom actually kind of looks like on the atomic level. Okay, so we're going to talk about electrons and their orbitals. Because orbitals are not perfect spheres, they're not even ellipses. They're kind of weird the way they look and work. So, like we were talking about in the last section, electrons can act like both a particle and a wave. So that gives them a lot of weird properties. Give me one sec. So like light waves, they can actually be bent or diffracted. So there's a lot of kind of weird things you can do with electrons, like you can do with light, that you can't really do with other particles, other bits of matter. Okay, because other bits of matter don't work as that wave. And there's a lot more kind of wiggle room, obviously, with a wave than there is just a particle. Okay, so diffraction is the bending of a wave as it passes by the edge of an object or through a small opening. So if you look at an object, okay, you can see its shadow, but you'll notice that the shadow has kind of two regions. There's that darker region, okay, and then at the edge of that darker region, there's a kind of more vague shadow. Okay, it's not as dark, it's still there, but it isn't as solid darkness. Okay, that is because of diffraction. It's because light is being bent around the edges of those objects. So not all of the light is getting around it, but not all of the light is being blocked. Okay, so that's why you kind of have the fuzzy edges along the edge of an object when you're looking at the shadow. Okay, it's because light kind of bends around the shadow a little bit, right? And that is diffraction. So electron beams, like these waves, can interfere with each other too. So if you actually drop a rock or something into a pond, you see the ripple effect start. Well, then if you drop a rock in a different spot but close by, that will also produce the ripple effect. And when those two meet, the waves that come out of that interfere with each other. So you're going to get different patterns. And electrons work the same way. Now this is where a lot of quantum engineering, all of that comes in. So electrons can act really kind of strange. And a lot of what we know about electrons, we've actually used what we know about light waves and things to figure out. So you get what's known as an interference pattern. So basically interference patterns are where if the waves overlap, like if their peaks overlap, you get an increased signal, okay? But if you get a peak and a valley meet, then it cancels out. So you'll get some regions where the electrons are coming in real strong, okay? So you get an increased pattern, or you'll get some regions where there's nothing there because you have an interference. And I do have a video about that that kind of shows more what I'm talking about. It's really weird. Okay, just a warning. But, alright, so moving along, we have valence electrons. So valence electrons are the electrons in the outermost orbital of an atom. Now, for most of the periodic table, it's relatively easy to figure out how many valence electrons are in each column, okay? Because if you start with the first column, you have one valence electron. Go to the second column, you have two, okay? Then you skip over the transition metals and go up to where boron is, and that is where you have 3 valence electrons. Carbon has 4, that column, and then you've got nitrogen, that column has 5 valence electrons. The next one with oxygen has 6, and then the fluorine, the column with fluorine has 7, and then finally the column that starts with helium has 8. So for most atoms, and we will see some exceptions to this, but for most atoms, they can only have up to 8 valence electrons. Now these valence electrons are the ones that are most important in the atom. They're the ones that actually control how the atom is going to react. Okay, so you've got one valence electron in that first column. Okay, those alkali metals are actually explosive in water. Okay, they react so quickly, so intensely, because they really just want to get rid of that one valence electron. Okay, and they will react with anything they can. And they can react with water. They can actually react with water in the air. So if it's humid, they can still explode even if they're not like in water. Okay, so some of the more intense atoms in that column, in that group, family, they are not, they're actually not allowed to exist in normal atmosphere, okay? And what I mean by that is that if scientists actually purify some of that compound, it has to be kept in a sealed container that is full of oil, okay? Which means that the oil blocks out the water in the air from getting in contact with that element, right? Because if it got in contact, then it would react explosively. So, yeah. So valence electrons, again, determine the chemical properties of an atom. So again, if an atom has one valence electron, it's easier to give up that one electron than it is to gain 7 more. Okay? So that determines whether it's going to become a positively charged ion or a negatively charged ion. So if it's easier to lose electrons than it is to gain to get to 8, okay, it will lose them and become positive, right? And this is all because you've got your valence electrons. The valence shell is the outermost shell. But for most of your atoms, you do have an inner shell of electrons. So if you lose all of your valence electrons, okay, you've lost that entire outer shell. Well, it now disappears, and the shell that was one inside of that is now your valence shell. Okay, so valence is just referring to the outermost orbit of an atom. Okay, so if you have some in there and then you lose all of those, you're not losing your valence shell, you're just changing which shell is the valence electron shell. Okay, now if you have 7 valence electrons, it's easier to gain 1 more electron to complete that valence shell than it is to lose the 7 that are already there in order to go down to the valence shell that's inside of that one. So electrons will always fill the lower energy orbitals first, okay? So they want to be in the lowest energy state possible. But once that shell fills, then they'll have to go into a higher energy orbit, okay? All right. Quantum theory. So quantum theory describes the wave property of electrons and other very small particles like photons. Okay, we're not going to go into a lot of the math there yet. Don't worry about that. It's awful, and that's me saying that. So yeah, it's bad. But hey, if you want to do it, go for it. It's awesome. Anyway, we are mostly going to talk about a couple of the theories that go into the quantum theory. So it is based on work by both Schrödinger and Heisenberg. So you might have heard of both of them, especially if you watch The Big Bang Theory. Schrödinger, he is most famous for the cat, Schrödinger's cat. It was a theory about basically you put a cat in a box with a sealed vial of poison that will break at some point. You don't know when. And then you close the box with the cat and the poison in there. And then until you open the box, you don't know if the poison has opened and killed the cat or if it's still sealed. Okay? So until you open the box, you can think of the cat as both alive and dead. Okay? So it's kind of this duality thing. It's kind of a weird concept, but it is this duality that is present in electrons when you talk about their particle aspects and their wave aspects, okay, because those are pretty opposite of each other, okay, so like living and dead cat. And then you have Heisenberg, the Heisenberg uncertainty principle, okay, that states that you cannot know both an electron's location and its speed at the same time. You can know one or the other, right? Now, fun thing about electrons is that when you observe them, you change them. It's great. Makes it real difficult to study a lot of this, okay? There is actually a joke about the Heisenberg uncertainty principle, but an electron got pulled over for speeding. Cop comes up and he says, "Do you know how fast you were going?" Electron says, "No, but I know exactly where I am." So the cop told him how fast he was going. Electron says, "Great, now I'm lost." I hope you got it. I think that one's really funny. I love it. Anyway, so electrons do not travel around the nucleus in neat orbits. They kind of can't. They have that wave property that makes things a little bit funky, okay? So what Schrödinger and Heisenberg did was they actually used mathematical models to kind of map areas of probability of where it's most likely that you're going to find an electron around the nucleus. And that's where these electron shells came from. Okay, so the orbitals are those 3D regions around the nucleus that indicate the probable location of an electron. Okay, and in this we oftentimes use orbitals and shells kind of interchangeably. All right. So there are 4 types of orbitals, and they come in different shapes, they have different energy, and there are different kind of orientations around the nucleus. So they are represented by these 4 letters. You have your S, P, D, and F orbitals. Okay, and so we're going to break this down a little bit more, but we're going to stop here and pick up in the next video.